Okay, well, we're going to start the second part. So we've talked a lot about hyperbolic geometry in theory, and that if you take a distance function or you take the closest distance between 2 points, we have much more complicated formulas, but there are some potential benefits, right, compared to Euclidean geometry. What we're going to talk about this part is some initial works in machine learning and then eventually a lot in computer vision that have tried to use these alternative ways of computing distances, etc. And then seeing what kind of benefits we might have for computer vision. So we'll go into, let's say, a short historical perspective until, let's say, roughly last ECCV. No, sorry, CVPR. So I thought it would be best to split it into 3 parts. So this, we cover the last 5 years in, let's say, in 45 minutes. So we start from graphs and trees and text. So the first, let's say, sources of success for hyperbolic geometry. And based on those starting points, we'll talk about the first works in computer vision, especially in the deep learning era. There have been, let's say, in previous eras, hyperbolic geometry for computer vision, but I'm going to specifically talk about deep learning with hyperbolic geometry. And then we'll cover the last 2 years where we see papers building on top of those initial works to make them better. So let's start it in 2017. Oh, this is actually a picture from 2020, so we'll reiterate a core point, which is that if we have a hierarchy, I have a problem with Euclidean geometry. They're not friends. So I think this picture illustrates it quite nicely. So if I have a hierarchy with 5 points, so 1 root and 4 leaf nodes, I'll be fine. But if my tree goes deeper and deeper, the number of nodes grow exponentially in my tree. And what happens in Euclidean geometry is that the leaf nodes, which are typically the ones that I care most about, come closer and closer to each other. And that's a problem, because I still want to do some sort of inference or recognition, so I still want things to be far away. So there's quite some distortion. And in theory, you could still, let's say, get around with them with an exponential growth of dimensionality or distances. It still doesn't work that well. So what people have been starting to do around that time was, well, all these tools of deep learning and gradient descent, can we use them, but by replacing the Euclidean geometry with the hyperbolic geometry? So I think this is quite a important paper in that regard. The paper is called Poincaré embeddings, and they said, well, we have word nets. Well, one of the deepest hierarchies we can think of that we've made. And I'm going to just embed it on a plane, and just any volume. Well, if I do it in Euclidean geometry, it doesn't work that well. So if I look at distances, they don't really represent the similarity in the word net hierarchy. So what they did was they said, well, we're going to use this Poincaré ball model, and every node in word nets becomes a point in this ball model. So a point in hyperbolic space, such that the position of these points represents the hierarchical similarities very well. And we'll talk about how you can measure this. So this is a 2D visualization of it. So if I have a 2D Poincaré disk, this how it starts, the training is on the left, and in the end it looks something on the right. Note that it looks like it's all on the edge, but that's because distances grow exponentially, so actually they are very hierarchical. It's just hard to see. So what they said was the following. So we have many nodes, and these nodes are connected with parent-child relations. So we have 2 sets, some set of nodes that are connected with parent-child connections, and the others are not connected. And what we want is for each node to have a point in hyperbolic space, such that they really abide by the hierarchy of word nets. So what did they do? They just made it into an optimization problem. So we have these representations and we want to minimize our loss over them. Note, of course, we want to make sure that they are inside the ball. So we want to make sure that for all of these representations, their norm is smaller than 1. And the main idea was for this loss to say, well, all the parent-child connections, we pull them together, and all the non-parent-child connections, we push them away. And that's all they did. But the main difference being that the distance function was different. So this distance function d was now this hyperbolic distance function, which looks more complicated, but you only have to implement it once and then look at it again. So given that, this looks more like the formulas that we are dealing with, right? So we just have a softmax over all these distances, and then we make it work. So this is the distance function on the right. And then we optimize for that. So we just transform it into a softmax loss that we can optimize over, such that as long as these parent-child connections are pulled and pushed, our loss gets lower and lower until we're happy. So we can do that, but we have to do one more change. You have to think about gradient descent. So normally you just take the gradient and you do descent. In hyperbolic geometry, that creates a problem, right? Because if a node is here and then I do normal gradient descent, it's just a straight point and it can be outside the ball. So you have to do what is called Riemannian gradient descent, which is gradient descent with some extra steps. So basically a static descent and do some scaling and projection. So make sure that it maintains inside the ball. So with these two ingredients, so you change the distance function and you change the gradient descent to this version of it, you can just make it work. And the differences between how well you can do certain tasks, given that you embedded this WordNet in Euclidean geometry and hyperbolic geometry, were quite big. So here you see a few examples. They did the reconstruction of WordNet. So if you leave a certain data of link prediction, can you predict whether these are parent-child connections, for example? If you look at the average position scores, or you also have a rank score, which I will focus on the average positions, you can see very huge differences. So these are quite compact dimensionalities for WordNet. It doesn't work that well for Euclidean geometry. There's always distortions. And perhaps with many, many dimensions, you will get a bit better. But the differences with the Poincaré results were quite big. You see, for example, at 5 dimensions, there's close to 0 MAP for Euclidean geometry. So when you construct WordNet, you reconstruct it as a task, well, it's already very high for in the 0.8 for Poincaré. Basically, the difference between it not working and it working in low dimensionality. And the same for if you do a link prediction task, you see the same kind of numbers popping up, where it just doesn't work for low dimensionality with Euclidean space, and it already works really well with hyperbolic space. And with more and more dimensions, it starts to work for Euclidean geometry, but it doesn't get close to hyperbolic geometry. And here on the right side, there are a few other data sets, or let's say not data sets. Oh yes, question. So for the link prediction, it just means, can you predict whether they are parent-childs, and then you can rank them according to how likely certain pairs are parent-childs, and based on that ranking, you compare to the ground truth, you get average position scores. I don't remember from the top of my head what the WordNet reconstruction MAP is, but it's something along similar lines, where you look at the ordering or the relations between them, and they have to match hierarchical similarities, or WordNet similarities. So basically, MAP is, let's say, the number of how well the original hierarchy was preserved at eye level. I don't know the details, but we can look it up afterwards as well. And on the right, you see some other, let's say, well-known hierarchies from other domains where the differences are similarly clear. So this woke quite a few people up. Like, okay, this might be a very useful geometry to do this kind of research in. So people have been playing around with other extensions of this kind of idea. So on the left is something called entailment cones. So they say, well, rather than thinking about it as parent and child, you can think about it that a tree has all these subtrees. Right? So I start with a big tree, and then if I go for one node, I have like a small subtree. And you can see it almost like an entailment, like everything that falls below it is like a smaller triangle or a cone in high dimensional space. So you can, they said, well, you can use that as a, let's say, a better way to preserve the hierarchy, rather than thinking about them as pairs of parent-child. You can actually think about them as smaller and smaller cones if you go deeper in the hierarchy. So that's, let's say, an improved way of representing hierarchies in hyperbolic space. And others have been looking around by just expanding them, right? What if you have multiple types of relations? What if you have just multiple relations in general? Trying to extend them to make them work with whatever kind of knowledge you might have at hand. So these are all works on that. If I have a hierarchy, can I embed them as well as possible? Well, that's a bit far away from computer vision, I would say. So let's take one step closer. Let's go to graphs. Also still far away from computer vision, but at least a little bit closer. If you think about a graph, they're latently almost a little bit like a tree. Sometimes there are some loops, etc. But there are some also, if you think about it, there might also be hierarchical, right? If I have a social network, or I have on the right, for example, I have a molecule, there might be latently some hierarchical structures in there. Well, the question is, if that's the case, then shouldn't we also use for graph networks, make the switch from Euclidean to hyperbolic geometry? So people have been trying it, and the first ideas in it were, well, what do? Is we assume these points are now in hyperbolic space. And to do this graph layer, what we do is we take the notion that Martin explained earlier of exponential map, and the inverse is the logarithmic map. So we take a logarithmic map from the hyperbolic space to Euclidean space, then do our normal graph layer that we all know, and then back to hyperbolic space with the exponential map. So this was around 2019. So this is what it looks like. So on the left you see a standard graph layer. So what do? We have a representation for a node U in the next layer, and that's just the sum over all its neighbors, where we take that representation of the neighbor with the adjacency matrix A and some learnable parameters W, right? That's what we learn in a graph network. So this is what a normal graph layer looks like. So what did they do is they added these two functions. So the input nodes are now hyperbolic, so you have to move them back to Euclidean, then do your normal graph operations, and then back to hyperbolic space. So that's, let's say, the first attempt. So, let's say geometrically it's all correct, but note that we're not really doing fully hyperbolic learning, right? Because it's actually an approximation. And what they showed was actually already doing it in this way, where we don't actually have to change all our normal layers. We just have to add these two functions and don't touch the deep learning part. It already works really well. So especially for molecular data, and when you have only a few examples, you can do node prediction or graph classification better than Euclidean space. Note that they're always doing it in these smaller settings, so with fewer samples. So the second generation, this is really more recent, it's actually quite ongoing research. It feels a bit wrong to go back and forth between Euclidean space and hyperbolic space. What I want is, if I'm in hyperbolic space, I just want to operate in hyperbolic space. So this is a CVPR paper from last year where they said, well, actually, yeah, we agree. We don't want to do this mapping and then your normal graph layer and then mapping back. So what they did was they stayed in hyperbolic space. And there you see the knowledge of all the different models coming to your advantage, because what they did was they assumed points are hyperbolic space. But you need to do a few things, right? You need to do a transformation, a neighborhood aggregation, and you need to do some nonlinearities. But they figured out that different models are actually good for different things. So they start in the Lorentz model for doing the transformation. Then you have the neighborhood aggregation. So they went from the Lorentz to the Klein model. And then they had nonlinear activations. And because you want some conformal thing, that the angle remains the same, they actually went to the Poincaré model. So I think it's fair to say that this is still ongoing work, because, well, you no longer go from Euclidean to hyperbolic space. I'll come back to you in a second. You actually have to move still within different hyperbolic models. So it still feels a bit wrong, but at least it's all within hyperbolic geometry now. But it's still ongoing. Yes? We have a question over there. So for this, they treat it as a hyperparameter. There will be a paper from a very recent literature that they talk about the importance of curvature. But I'll come back to that. Let's say 20 minutes, there will be a paper on this. So most papers, they treat it as either just have a unit curvature, negative curvature, or they have it as a hyperparameter. They keep it fixed. But you can learn it, but that, I'll come back to that. So that's where we are, let's say, in graph networks. So we are able to do graph layers in hyperbolic space, although perhaps not in one model yet, but might be a paper for you to write next. At the same time, we have seen the development of hyperbolic network layers. So a few pivotal papers, and these were hyperbolic neural networks. They provided, let's say, the outline of how to do logistic regression, so how to do your classification task, how to do feed-forward layers, and how to do recurrent layers in hyperbolic space. For these last two, there were some caveats to that. So for logistic regression, you need more parameters than you would have for logistic regression in your Euclidean space. And for the feed-forward, they did the same trick as the graph layers. So you go back to Euclidean space and do your normal feed-forward and then back to hyperbolic space. Last year, there was a paper, well, it was very clearly inspired by, so the ++ version of hyperbolic neural networks, that showed that you can do logistic regression in hyperbolic space just with the same number of parameters as your Euclidean logistic regression. And also they provided the foundation, although not implementation yet, of how to do convolutions in hyperbolic space, which is of course what we very much care about. So they also showed a picture, so this is just how different it looks if you do this trick from going back and forth between Euclidean and hyperbolic space I think this is a linear layer or a hyperplane. It looks very different with what you get. So it's very important to really stay in hyperbolic space when you do this kind of thing. So as you can see by the dates, this is very recent work. So we talk about summer last year, where we have the first theory of logistic regression just with equal amount of parameters and just at least an outline of how to do the convolutions, but no convolutional images yet. So the design of these and the continued effort of making different layers hyperbolic is ongoing. But while that is still going on, it didn't stop us from already trying things out in computer vision. So I'm going to talk about CVPR 2020, which I would say is the conference where 3 ideas, the exact same ideas from different directions were viewed. And I think people talk about replication as being a bad thing. I think it's a very good thing. If 3 different groups come with the same idea at the same time, there's something going on. So I'm going to talk about these 3 papers, and then Mina will remotely take over for the last part of all the papers that have gone further with this idea. I'm going to talk about hyperbolic image embeddings. And well, we didn't have any convolutions in hyperbolic space, etc. There was this, you can do logistic regression on or you have these exponential maps. Is that good enough for us for computer vision? So they had an hypothesis. They said, well, whatever data or labels you might have in computer vision, very often that's hierarchical. In your image, it might be latently, right? They say maybe there are spatial structures or there are subcategories or anything in your pixels already. But in your labels, most certainly, that can also be the case. So that on the right, you see what is called a delta hyperbolicity test. So what you need to know about this, the lower the number, the more hyperbolic a certain collection of elements is. So what they did is they took a network that was not trained in a hyperbolic way, but Euclidean, and then check for how hyperbolic it is. So it was not trained to be hyperbolic. Sorry? So what they did was for all the images in the data set, they feed it into a network, so you get Euclidean representations. And then they did what is called a delta hyperbolicity test. So they looked at the distances between them and see whether that conforms more to a Euclidean or hyperbolic geometry. And it conforms more to hyperbolic geometry, which is a little bit surprising, right? Because it wasn't trained that way. And I thought, okay, that's evidence enough to play around with hyperbolic geometry for computer vision. So what they did was the following. So they took a data set, and you have your normal convolutional network. So you start with your normal layers, your Euclidean layers. So you input an image, you feed it into a network, and your output is a representation, right? A d-dimensional representation in Euclidean space. Then they mapped it to hyperbolic space with the trick that, we can call it a trick now, it's a more theoretical background, but for us it's a trick. We move from Euclidean to hyperbolic space. I'll go to it in 1 second. And then we have a prototype, we can maybe get prototype by averaging. Yeah, question? Sorry, can you repeat the? You mean this table? So it means that distances between the representations conform more to. What's the shortest answer to this? Maybe Martin, you have a short answer to this. I would say it conforms more to how distances should operate in hyperbolic space, but I'm not sure if that's the. Yeah, I think that's the shortest answer to what it should be.
Testing the structure of the metric space, and then you can determine whether it's closer to Euclidean, closer to hyperbolic.
So whether the points themselves conform to the metric space that you have, either Euclidean or hyperbolic. So they did these 3 steps. So you have things like prototypical networks that work for few-shot learning, etc. So what they did was they said, well, we want to do that, but then in hyperbolic space. So your normal convnet is just still Euclidean. We don't touch that yet. That's too difficult. But the output space is Euclidean. Then do the exponential map to hyperbolic space. And then you can do distances or averaging, these kind of things with hyperbolic operators. So in this case, they made prototypes. So if you have a few-shot learning, you have 5 examples of a certain class, you feed them to a network, to hyperbolic space, and then average in that space. So you have a prototype for a class. And if you have multiple classes, then if I have a test sample coming in, I can compute the hyperbolic distance to all these prototypes, select the nearest one, and do few-shot learning that way. And I did some simple tests, and they showed actually, especially with a small network, it's better to have the output space be hyperbolic than Euclidean. They have a few more cases. In their paper, their caveat was, yes? Okay, so about this picture on the right, this is a visualization of their paper. They showed, I think, both MNIST and Omniglot images. They just projected with the same network to the same hyperbolic space in 2D. Yeah, I think it would be a bit latent, the hierarchy there, because I think MNIST is not really that hierarchical. But they show that certain things are digits that are visually similar are also closer in that space. So I would say that MNIST is a bad way to think about hierarchies because, yeah, you have 10 digits. You can force it to have some hierarchy, but it's very limited. But I did show that there was some grouping and that certain digits that are visually similar also grouped a little bit more. But this is, let's say, the 2D output space in hyperbolic space. So they showed, in all fairness, that if you have a really deeper rest net, and then hyperbolic space, the differences become less favorable for hyperbolic space. But with a small network, it's better to have hyperbolic embeddings than Euclidean embeddings. Likely because the space is more compact, you get more use out of it, similar to what we saw with the WordNet reconstruction. Some side benefits that they showed, so on the bottom you see an image with in and outer distribution. So you train on one data set, and you test by feeding 2 data sets the test. And you see quite a discrepancy between, in this case, MNIST and Omniglot. So you might be able to already do some outer distribution detection for free. So there might be some benefits for uncertainty in outer distribution detection that they saw. And other papers have gone into this in more detail. But they were first to show, okay, there's some potential benefits there for if you want to do out of distribution detection or have some uncertainty information in there. So basically, I think they showed the distance to the origin as, let's say, a measure of uncertainty. So at the same time, there was another paper that has a very similar intuition. If I have a hierarchy, well, that's super useful information. And we know from these other papers that the hierarchy is better embedded in, let's say, the Poincaré models for hyperbolic geometry. So if we have that, shouldn't we use hyperbolic geometry for zero-shot learning? So what I did was the following. Same idea. An image, feed it into a normal network. We don't touch that yet for hyperbolic geometry. And then do an exponential map. They did a Mobius transformation layer, so maybe one more linear layer in hyperbolic space. But the same idea holds. I have an image. and first a normal network and then to hyperbolic space to have it as a point in hyperbolic space. And then at the same time, I can have a hierarchy, let's say like WordNet, embed that with the Poincaré embedding we saw earlier to hyperbolic space. And now both the hierarchy and images are points in hyperbolic space. So if you keep the hierarchy fixed and make sure images go towards their own class with the hyperbolic distance, you can train on seen classes and then generalize hopefully to unseen classes because you preserve the hierarchy with the Poincaré embedding. And indeed that was the case. So they showed on ImageNet if you have the WordNet, so ImageNet is derived from WordNet, so you can take the ImageNet hierarchy itself, embed that in hyperbolic space, so they become all points in hyperbolic space, and then you minimize the distance between your image and the label of the image during training. And then you can do zero-shot generalization. And especially when making small mistakes, this was also very useful. So they see these 2 hops kind of metrics. What it means is you can evaluate whether I predict my own class as being correct, but I can also say, well, if I at least have my parents correct, right? If I have one of the other children of the same parent, am I correct or not? And because you enforce the hierarchy, almost by design, you do better on these kind of metrics. And this has also become quite a hot topic in hyperbolic learning. If I have a hierarchical goal, or I have hierarchical constraints, then it's better to have to embed the hierarchy and use hyperbolic geometry. You can think about, for example, medical domain, right? If any mistake is costly, but if I have a disease and I predict there's another disease that's costly, but not as costly as saying I'm healthy, right? So there's a certain cost matrix that's also hierarchical that you want to enforce. So the third paper, at a very similar perspective, exact same idea, but now from the video domain. They said, well, all these video datasets, ActivityNet, moments in time, all these kind of datasets, they have hierarchies on their websites. They use it to say this is how we construct the dataset, but they are left untouched. No one uses them hardly, with few exceptions. They said, well, what if we take this idea of the Poincaré embeddings and feed it into the video domain? So this is how it roughly looks. So they did the Poincaré embeddings on the left. I think they did the entailment cones. So they just have a hierarchy of actions. Let's say you have a specific action that is, let's say, a sports action, and then it forms a hierarchy with other actions. You embed that hierarchy into hyperbolic space, and you keep that fixed. And on the other hand, you have a video. You do your video network, again, Euclidean, until your video is compressed into a representation. Again, that you can move to hyperbolic space with the exponential map. And now both videos and these action hierarchies are points in hyperbolic space. And I can, again, just minimize distances. And they showed, well, one very nice benefit of doing this is that my dimensionality of the output space is no longer constrained to number of classes. So this is, I think, I'm not sure which data, but there's 200-dimensional output space because there are 200 classes in the dataset on the left. And then if you just use your normal, they did ResNext as let's say the backbone. If you add a softmax cross entropy on it, your last layer needs to be 200-dimensional because I have 200 classes. But if I take this idea of having the output space be hyperbolic and just every class is a point, then I can just choose my dimensionality for free. And because we know that hyperbolic geometry is very compact, so good performance at very few dimensions, you see that back here. So you can have much lower dimensionality while maintaining most of the performance. And here they have a sibling and cousin MAP. It's the same as this hop MAP, where they say, well, it's for sibling MAP, my prediction is still correct if at least the class I predict has the same parent, and cousin if they have the same grandparents. That's why the numbers also go up. So you see also that with these hierarchical constraints, it's better. On the right, you see an image of what the embeddings, the pairwise similarities between videos look like if I train it the normal way or if I train it with the hyperbolic way with the hierarchy. And what you see, if you train it in the normal way, so these are the average pairwise distances between the videos of a class. So you see some patterns popping up, right? So you see some small squares perhaps popping up, but it's very noisy. It's also high similarity to completely unrelated classes. So you could say you don't, by design, learn hierarchies. But if you enforce it, so what you see on the right, of course, you have the highest similarity to yourself, but then you see these squares popping up. And these are all subtrees of the hierarchy. And because you enforce the hierarchy a priori and you keep it fixed, you actually have a very nice hierarchical working network afterwards. And I think that's where we are right now for the first, let's say, that's what the 2020, 3 ideas, exactly the same setup, Euclidean network, exponential map, and then doing some things in hyperbolic space with distances. And both from the image and video domains, from supervised and zero shot, we saw some benefits. And with that, we want to move towards papers that have, in recent, let's say, last 2 years, have tried to improve it. So we'll show 4 axes. Mina will take over from here. She cannot join here in person, unfortunately, but she can join remotely. So I'll ask people if we can take over for Mina. And I guess I will have to do the clicking. Hi, Mina.
Hi, good morning.
Or maybe you can share your screen. That might be easiest. Sure. We have all morning. Yes.
Can you see the screen now?
We can see your screen. Thank you. You can start.
Good morning, everyone. I think this is going to verify Zoom. So after the initial hyperbolic visual learning, we will talk about the recent papers hyperbolic visual learning after 2020, which is just methods moving towards better, stronger, and faster hyperbolic visual learning. So we'll talk about the recent approaches via different means whereby just 4 different directions: visual learning, network learning, and structured messaging. First is the start of visual learning. The main idea in visual learning is to learn and reading space through the dedicated example, theory that visual general is done to all examples too. One of the task, different curvatures are learned. So just via this, you can have different curvature values. You can have just you can learn the intrinsic geometries for different data structures. In the right side, you can see a table including just different tasks, different visual learning tasks, and different curvature values.
So there are three different curvature values: curvature 0, and two negative curvatures. Curvature 0 is Euclidean space, and negative curvatures stand for the hyperbolic space. And three different few-shot learning tasks. For the first few-shot learning task, the curvature 0, which is just Euclidean space, is performing well, while for the two other few-shot learning tasks, the negative curvatures, which are hyperbolic space, which stand for hyperbolic space, are performing better. This can show that the fixed curvature assumption is not always the best assumption and is not suitable for all the data structures. And instead of that, we can just use task-aware curvature values and to learn better geometries. And curvature is really a vital parameter when learning just meta-learning and when learning embedding space for different tasks. Although hyperbolic embeddings are working well in few-shot learning, but still there were some questions after the first approaches. So one question is that how the hyperbolic embeddings are performing in standard benchmarks. And then just the other one is how to perform optimization in our few-shot learning method. As you can see in the right part, you can see a hybrid architecture performing few-shot learning. So what do we mean with hybrid architecture? For architecture, first there is Euclidean space, which is just extracting the embeddings of the input image, and then the Euclidean embeddings using exponential map are projected into hyperbolic space. And then in the hyperbolic space, the loss value is calculated, which can be backpropagated to the Euclidean space and to perform optimization. In the left part of the figure, you can see a 2D output space of our hyperbolic embedding space. Different colors show different data points, and the movements here show how the embeddings are changed during training. As you see, optimization pushes the points towards the edges. So when just initializing from random embeddings, they are somehow closer to the origin, but when performing optimization, the embeddings move towards the boundary. We have talked about the boundary of hyperbolic space. As you go closer to the boundary, the distances grow exponentially, which can result in a large training loss. As you can see in the middle figure, as the epochs are closer to the 9, the training loss is suddenly increasing. And now, when backpropagating this training loss, something strange is happening, which just gradient value, instead of increasing, is still decreasing, which shows gradient vanishing is happening. And the reason lies in the going closer to the boundary of hyperbolic space, and then just backpropagating the loss value to the from hyperbolic space to the Euclidean space. May et al. Just investigated this problem and showed that if we want to just deal with the vanishing gradients, one simple solution can be limiting the embeddings not to go very close to the ideal boundary. So then just we will limit our output space in a way that just the embeddings will be not very close to the boundary. And then it will result in it will solve the vanishing gradients problem. The result will be improved in few-shot learning, and also it will bridge the gap in standard image classification benchmarks. The second axis is hierarchical learning and inference. You can see 3 different samples of a butterfly dataset. For the dataset, we have 4 different levels of granularity. The first one is family, then subfamily, a species, and genus and a species. While we care about the most specific level of hierarchy, which is a species, we also just often care about the multiple levels of granularity, the family, subfamily, and genus too. So our goal is to just have good performance via all these different levels of granularity. how can we perform this and how can we use this? So we have the hierarchy for in different levels of granularity, and one solution, as we have talked about the hierarchical embeddings in hyperbolic space, one solution can be embedding these data in hyperbolic space. Also, when using just order preserved embeddings, it can improve the hierarchical recognition and learning in different levels of multiple levels of granularity, which just works especially very well in hyperbolic space. What about other domains? Pascal talked about medical domain, which really just the errors in medical domain can be more vital, more important than the other domains. Can hyperbolic space have benefits in medical domain too? Again, in medical domain, most of the approaches assume that the data, the class labels are independent and they have no relation to each other, while it is not true. As we have seen for most visual data sets in medical image, it stands to. The classes are semantically related and they can have some hierarchical relation between them. In the left, you can see just hierarchical embedding for skin lesion disease. So just it is from the more general diseases going to more specific ones. So when embedding these data into Euclidean space, we just assume that the data points, the classes are all independent, while it's not a correct assumption. We can use class hierarchies and we can embed them in hyperbolic space too. How should we perform it? So in the right figure at the bottom, you can see class hierarchies. First, using Poincare embeddings, the class hierarchies are embedded into hyperbolic space. Then when learning the representations for the input image, we can learn the representations in a way that the goal will be having closer representations to the learned hyperbolic label representations, which are based on the hierarchies. So with this solution, we can just include the class hierarchies inside our classification model. But what are the benefits and why should we use this? So one benefit of adding class hierarchies inside a model is boosting the performance and having better performance, but also, as we talked about the errors in medical domain, the errors are really vital and just we want to have, for example, just instead of predicting a completely unrelated disease, for example, we prefer to predict a more general but somehow correct parent of the class label. So we like to have less severe diagnosis in medical domain, which including class hierarchies and embedding it in hyperbolic space can help us to achieve this. Up to now, we talked about the hierarchical structures of the data points, and we told that because most of the data, the images, visual data labels are hierarchical in nature, it is really good to embed them in hyperbolic space. But using hyperbolic space, because of the curved geometry, can have some difficulties. For example, when using Euclidean space, there are some kernel machines, there are some kernels which help us to have better representations, and also just they have a lot of theoretical background, which with using kernel machines we can use all the theoretical backgrounds too. What about hyperbolic space? Can we use kernels in hyperbolic space too? As Van Gatal investigated, the answer is, yeah, rest assured, your favorite kernels also work in hyperbolic space too. So this paper shows five different kernels in hyperbolic space: hyperbolic tangent kernel, hyperbolic RBF kernel, Laplace kernel, and generalized hyperbolic Laplace kernel, and hyperbolic binomial kernel. The experiments in this paper show that you can first plug these kernels on top of any network, and then based on the experiments. These are helpful for different challenging applications like few or zero-shot learning, person re-identification, and knowledge distillation. The next question can be about the boundary of hyperbolic space. We talked about the ideal boundary, which is where the distances are infinite and we cannot use it. But is there a solution to place embeddings on the boundary of hyperbolic space? Buseman distances enable this. So with the help of when we use Buseman distance, which is just a distance function in hyperbolic space instead of hyperbolic distance, then we can place representations on the hyperbolic boundary too. We call these representations ideal prototypes. So the goal is to just have, for each class, we will have points on the ideal boundary, which we call them ideal prototypes. And then just we will perform classification, and everything is just like the other methods. The embeddings are inside the hyperbolic space. The goal is to just have embeddings closer to the class prototypes, minimizing the distance. But with the help of Buseman distance, we can place the class prototypes on the boundary. But what are the benefits? Why should we care about the boundary, ideal boundary? So performing prototype learning on the boundary using ideal prototypes improves the results over other prototype learning networks. Also, it provides interpretable embedding space. Here you can see just two-dimensional Poincare disk embedding space of our classification method. The samples are from CIFAR 10 dataset, so there are 10 class prototypes, in each prototype indicating a class, and the points inside the space show just different image representations after training. So as you see, the representations tend to be closer to the corresponding class prototypes, but also there are some misclassified wrong samples too, which their position on the hyperbolic space indicates that just they are wrongly classified or they are uncertain. Up to now, most of the hybrid structures were on top of convolutional neural networks. But there are a lot of progresses in recent years, especially in using vision transformers. What about mixing hyperbolic representations and adding hyperbolic space on top of vision transformers? Can hyperbolic space have benefits there too? Ermolov et al. Has considered investigated hyperbolic vision transformers. So the first step, the goal is to have for different images from the same class label, the goal is to have representations which are close to each other. As the first step, the data points are fed into a vision transformer, then dimensionality reduction is performed via a fully connected layer, and then the resulting Euclidean embeddings are projected to the hyperbolic space using exponential map. And the loss function, or the goal, is to just minimize the pairwise cross entropy or pairwise distance between the representations of the images in having the same class. The experiments show that hyperbolic metrics are highly effective on top of vision transformer 2, and just when performing experiments on different well-known fine-grained data sets, hyperbolic vision transformer is the new state of the art. The next axis is structured prediction. Most of the works up to now were on the class level, so we were trying to classify image. It can be in different levels of granularity, but mainly just we will considering the relation between classes of images. But there can be other tasks like object detection. So again, the question is, can hyperbolic space perform well generalized to object
Hi, Mina.
levels.
Sorry to
Hi.
do, I think for the sake of time, let's do access for a bit of a high level,
Okay.
let's say overview. So we have to, let's say, do a few more minutes and then we can go to the questions and another break. Okay, thank you.
Sure, sure. Yeah. So to check this, to investigate this, 3 different types of object detection methods has been used, and then just the Euclidean embedding is extracted using the object detection method, and it is just projected to the Euclidean space. The results, again, on different type of object detection methods show that moving to hyperbolic embedding and using the hierarchies can help to improve the results. The next question is to just generalizing to pixel level. So can hyperbolic, based on computational costs or just based on the generalization ability, can hyperbolic embeddings generalize to pixel level? Hyperbolic image segmentation, which is the CVPR 2022 paper, shows that you can use hyperbolic logistic regression on top of hyperbolic Euclidean segmentation model to generalize well to generalize to pixel level. So the benefits of hyperbolic image segmentation is reach uncertainty information for free, and also better generalization to zero label comparing to the counterpart Euclidean methods. Also, just uncertainty can be one of the outputs of the segmentation, but also you can use it as loss function, so as a weight and loss function, which just will result in consistently improved state-of-the-art segmentation results and just better segmentation. Yeah. In this section, in the second module, we talked about the embedding trees, graphs, and text, which just hyperbolic deep learning shows a great promise. And then after just the trees, graphs, and text, moving to the visual data sets due to the hierarchical nature of vision data sets, hyperbolic embeddings just work very well in visual embedding too. And then the next step was just to how hyperbolic embeddings move towards stronger methods in different accesses like few-shot learning, metric learning, and hierarchical and structured learning. That's it. So if there are any questions. I cannot hear anything.
Hi, thank you for your talk. So in some of what you presented, it sounds like for image classification and embedding representation tasks that there's this advantage that comes into play when you have this hierarchy that is part of your representation space. So a question about the hierarchical structure of your classes, for example. Does that hierarchy have to be explicitly known ahead of time? So for example, do you have to have an explicit mapping of that hierarchy, or is that just naturally emergent from the classes that you train on?
Yeah, so right now we are at a level where you have to give it a priori. There are some works, so the next part will be on unsupervised learning, including some on clustering, where you might be able to recover or just automatically discover certain hierarchies. But right now what we have is we assume there is a hierarchy, and then we impose it in our network. But indeed, that's yes, it will sounds like an interesting direction to maybe have a hybrid where you have only partial or you want to learn it along the way. But right now, it's you have to enforce it.
Great talk, thank you, both of you. I've noticed that most of the networks that were tested in the hyperbolic case, they were regular networks with the Euclid embedding, and then there's the exponential map.
Yes.
Other cases that the entire net is non-graph cases, the vision cases, where the entire network is hyperbolic, or can you highlight these cases if I missed them maybe?
Yes, there are, but if I tell you, I have to kill you. I cannot tell you yet. It's ongoing work. So what we have right now is that computing distances, you can just take that function that we saw, distance function, and just write it out, and you can just work with it. But having real convolutional layers requires a lot more effort because you also have to do things like nonlinearities, normalization, all these kind of things. So the theory is out there right now, but it's yet to be fully implemented. But right now what you see people going further and further back, so more and more, let's say, linear layers in hyperbolic space, but let's say from the pixel level is yet to be done. Yeah, that seems like whatever happens there, it happens, but we don't know yet, but that will be an interesting direction. Yeah.
Thank you very much for the talk. So just I saw most of the talk was about hierarchical, but towards the presentation of Mina, the concept of uncertainty also emerged. And would you comment on the relationship between hierarchical and uncertainty?
Yes, I can, but maybe Mina, you can, did you hear the question, Mina?
Yeah, I hear.
Okay, maybe you can also show with some slides some examples of.
Yeah, probably this can be a good example. So the figures here, the circles show the hyperbolic output space, and each black dot is embedding of 1 pixel in the image, and different colors, for example, just greens, blues, each color shows one class in our hierarchy. So the leaf nodes, which are our goal classes, which we want to just classify them, those are very close to the boundary of the space. But as you go from the boundary towards the origin, the classes go from the nodes go from the more specific to more general. So when the pixel embedding is very certain, it will go towards the boundary, but when it is uncertain, it will tend to go to the parent nodes, which are more general ones, and then just the result will be an embedding more close to the origin. And then just we can find out that it is not certain.
Yeah, so to complement the answer, what we see is a very clear relation between how close is a point to the origin and how ambiguous is that example. So you have an example that is not typical, you'll see that it gravitates towards the origin and becomes, if it's more prototypical, then it goes more towards the boundary. And that is, of course, partially by design because we embed the hierarchy in similar way where the root is at the origin and the specific node, leaf nodes are at the edge. So this is partially by design, but also other papers have shown just by naturally, there's a very interesting property of the norm that you can use for out of distribution detection, or in this case for segmentation. You can even, they just show that you can look at every pixel, the norm that it has in the hyperbolic space. And if Mina, you can maybe show the picture of the uncertainty with segmentation. So the middle row is just, if for every pixel you plot the norm, just from one forward pass. And you very clearly see some patterns popping up. That pixels close to the boundary of objects gravitate towards the origin. Which there was not trained explicitly to be that way, it just naturally gravitated to do that. You can do it the same way in the Bayesian way, like on the right side. You would need many passes to the network with like MC dropout to make it work. But you get very similar pictures. It's almost for free, this uncertainty information, because it's from the path of the network. You can do it similar in Euclidean networks, but it doesn't work as well. So there seems to be some very interesting properties of the norm with respect to uncertainty.
Thank you.
Any more questions before we take another break?
Yeah, the last one.
Oh, last break, yeah.
If I may. So it's regarding this last thing you said and building up on top of the other questions. This is more of an opinion rather than a question what I'm going to ask. So it seems that the main point of focus in these in all of these papers is the fact that, okay, in Euclidean space, you're really bounded. So unless you have very high dimensionality, the distance between points is not, you know, as, let's say, significant as you would like. The thing is, though, that it seems typically we really like Euclidean approximations. So even, you know, when you work, for example, with manifolds, you just look at locally each part is a Euclidean space and you work there. So my question is, do you actually think that hyperbolic learning can like provide a new paradigm, or let's say, can it just be approximately as good by just using some kind of Euclidean space? For example, in graph neural networks, what happens if you have a hierarchical message passing structure? Because if you have the default message passing structure, it's not going to work. But what if you have a hierarchical, let's say, learning paradigm? How does that compare, in your opinion? Or in the future, will it be enough?
So I'm going to couple your question to the earlier question about why is only the last layer hyperbolic. I think there might be potential for a real paradigm shift where it just can learn things that Euclidean space cannot. Right now, what we see is that with only the last layer being hyperbolic, you see as the dimensionality decreases, you see a difference popping up, but with many, many dimensions, Euclidean is also very viable. So that's what we see right now. But yeah, that's only one of the 50 layers or 100 layers. So what happens if we embed it fully in hyperbolic space? Does it also get the same patterns, or is it completely opens up new doors? That we don't know. And I'm very curious to find out, but that, we cannot answer this question right now. The conservative answer would be there are benefits greatly at few dimensions, and the hierarchical relations are better preserved. The optimistic answer would be there's also really a way to learn other things if you make it fully hyperbolic. That's the hope, at least. There was one more question from the Q&A. That was about how deep is the deepest hierarchy that's being embedded in hyperbolic space. Well, for computer vision, it would be something like ImageNet, the amount of layers. But I mean, overall, we have WordNet embedded. I don't know how deep it is, 20 plus layers at least. In the hierarchy that's being embedded. So they can get quite deep, and the deeper it goes, the bigger the benefits of hyperbolic space, because the more you get the annoying parts of this exponential growth of nodes. So depth is not a problem for hyperbolic geometry. Actually, the deeper the better. With that, I suggest we take another, let's say, 15-minute break. I'm not sure what time it is. Let's maybe 11:40 we go back for unsupervised learning, right? How does it work with our generative models or self-supervised models or clustering? And then we'll hear from Jeffrey. So thank you very much.